everyone, welcome. I'm Bort. This video is about upgrading my wheel loader sound module. I hope you'll join me. Some of you may have seen my Volvo dumper unboxing video, but I have not yet introduced this machine. This is an Eagle Machinery WA470/Cat 980K wheel loader. Those that are astute observers may note that I've already made some changes to it. So I've already done a lot of cosmetic work to this. That includes a straight edge general purpose bucket. I have, and this is a functional mod, I've ground the forks that come with it so they have a little bit of a point to them, and found out that this is actually really good steel. It took a bit to grind it down. I have cleaned up the wiring around these work lights and around the cab, and inside the cab I've done a lot of work to hide the wiring. These are 3D prints that I sanded down and painted. Painted the fenders. I 3D printed the optional fenders, painted those, added mud flaps and painted the steps, and I'm sure half a dozen things that I'm forgetting. Oh, I added a battery monitor because it doesn't have anything like that. So a little preview of what will be in an upcoming video. I'll be going over those mods in the Volvo dump truck in some detail. For now, this video is about replacing the sound module. The sound module is buried in here. This is going to be a chore. And why do I want to replace the sound module? Well, this wheel loader has the same sound module that Eagle Machinery puts in all of their models, be it a bulldozer, an articulated dump truck, or whatever else. And it is a highway truck sound module. It doesn't really sound appropriate. It sounds strange to me, to the point where it actually kind of detracts from the experience a little bit. So I'd like to do something that will bring the sound a little more in line with what the vehicle is supposed to be. I decided on the Bayer sound module. This comes from a company in Germany. I will put a link in the comments below. If you buy the basic kit that I did, it comes only with a couple of servo cables and an IDC ribbon cable to break out the output functions for lights and such. And that is one of the reasons that I chose this module. The sound module, the stock sound module, doubles as a lighting control module. There are multiple challenges associated with this project. This module has an intimidating number of options for inputs and outputs and different sorts of functions and function groups that can be assigned. It's really a little bit bewildering, and it'll take me a little while to work through that. For the moment, I'm going to stay with some basic light outputs, and I'll try to adapt the original servo inputs from the receiver to the input mapping here. The biggest challenge, however, is that this module, as compact as it is quite a bit larger than the original. The original occupies the same XY footprint as a typical RC receiver and is only 1/4 inch thick. This is far larger than that, so I'm not really sure where to put it. I've had some ideas, but none of them are perfect. So once there's a battery in here, this underhood compartment is pretty full. There really isn't room to stick anything more in there. There are a couple of locations underneath that might work, but then I'm contending with some of the hydraulic lines and movement related to the articulation, and could have interferences there, as well as exposure to the elements from underneath. This is not sealed. There is a potential for a mounting location under here, under that plate in the front, but again, there's exposure to the elements, And at that location it's kind of remote from the rest of the electronics, so there would be a lot of cabling that would have to go in between. The location that I think I'll use, and it took me a long time to reach this conclusion, is in here in the back of the cab. I've done some exploration in here already and came to a couple of conclusions. So one is this big bundle of wiring can be eliminated. This is just a bundle of excess length from all of the various light and control cables. The RC receiver is right here under the battery platform. The sound module is right under that. But in here, in the back here, is a little compartment inside the back of the cab that is isolated by a piece of this black painted sheet metal. And it just has wiring and stuff in it, and it looks like that's what it's for. It was created just as a place to put excess lengths of wire. But if somebody wants to put in a little bit of time to cut all of these wires to length so that they don't need all of this bulk, then all of a sudden there's some space available in the back of the cab. And that is where I think I want to try to wedge in the sound module. This ESC and these wires from it belong to the wheel drive motor, which is right under this, under a mounting plate. If I can avoid cutting these wires, I'd like to. I want to see how much I can work down under this mounting plate without causing any interferences like rubbing of the motor's exterior armature on the wires. This cable goes to the beacon. This bundle here, I already know from previous experience, goes to the 4 cab lights. This bundle goes to the 4 corner chassis lights, front work lights and tail lights. This is the signal to the ESC, I think the motor drive ESC, that is passed through the sound module under the RC receiver, which is this box right here. This looks like another pass-through for another servo channel that is just unused, and they've just plugged it with hot glue. They really don't want anybody messing with this wiring and calling them up, "Hey, why doesn't my stuff work, man? I want a warranty replacement." The next round of destruction is to remove the battery monitor that's in here behind Bobby Joe Driver. This was my own installation. It used the battery pack's balance connector to read the voltage on every cell. But I won't need it because the sound module integrates that function. Alright, I just went for it off camera. The battery monitor, which came apart, was stuck to the back inside wall of the cab with my favorite double-sided tape, and there's a reason it's my favorite. Okay, here is the little metal doohickey that separates the cab interior from this electronics compartment. Now I can stick my hand straight into the cab. What I hope will be the last bit of destruction is to get this stack out. This is the RC receiver and the original sound module right under it. They are at least hot glued in, and I don't know about what else might be in store for me. I was poking around with this thing, on this thing, a little bit off camera, and realized that I had forgotten to label this 4-pin connector here. And when I traced it through, I realized it comes back here to the little speaker box. But there are 4 wires in this connector, and I pointed a flashlight down here, and I was able to see what appears to be 2 discrete speakers. And the Bayer sound module only has 1. So this needs investigating to see what I'm working with here. More taking apart. Alright, since I only have 1 speaker output, I am going to use 1 speaker. So I will just split this ribbon cable. And set these aside for the moment. Now I've taken the dual speaker setup out of here, and I cut all these cable ties and pulled this 4-wire speaker cable out of the harness that was there. I put the 2 wires from 1 speaker back in, and I pulled the this extension for the taillights up this way, and I've retied these, or replaced the cable ties, and I've left them loose for now so that I can adjust the cable lengths. And I am going to stick one of these speakers back in here somehow or another, probably with hot glue. Alright, I stuck the other of these speakers inside this cavity in the bottom here, up against the hydraulic fluid tank, with my favorite double-sided tape, not hot glue. Now I think, since I've already mapped out the channels on this, I can go ahead and disconnect the sound module from the receiver. The sound module is connected to the receiver with, looks like three different channels here. Channel 2, 6, and 7. Oh, and there's another, channel 9. Now on this spiffy divider thing, I've cut a very crude hole here for the micro SD card to slip through. I have drilled new holes in the back of the cab that are higher up to accommodate the additional height here. So I think I'm ready to test fit this. Now this is the speaker output cable that came with the sound module. I forgot to mention that part initially. And looks like I can't plug it in. Plug it in, plug it in. Alright, good sign. We have the right indicators on the power module, so it's getting power. Let's see. It is passing the throttle straight through without the arming control that the original had. But I think that I should be hearing some sound, and I'm not. Ah, there we go. I don't have it set up right. So there's some configuration work that has to be done, but at least it looks like everything's hooked up right so far. Next is the lights. The lights are on this nifty ribbon cable that I will plug in thusly. A bit has happened since I turned the camera off. I had forgotten to put series resistors in line with the LEDs, so I've added those. I'd recommend 330 ohm if you're using a 3S power system the way that I am. I've tucked some of the dangly bits over here, like the antenna wires and the filtering for the BEC inside here in some extra spaces. And now I am ready to try to bundle this stuff back up and see if I can get it in here without having to cut all of these wires down as I had initially expected to have to do. Alright, I have this thing back together now. As you can see, I've had a little bit of time to mess around with it, a little bit of time to spend configuring it, and I am really impressed with the amount of configuration that's possible. It has all kinds of different channel assignments and mixing for lights and sound and other output functions that I'm not using. It's pretty amazing. Let me show you a little bit about it here, how I have this set up. As before, let's see if I can do this backward. The rocker switch here is on and off, though it doesn't require that to be able to start and run. Start the engine, and then we got what, forward. Reverse. And then I have some other kinds of functions set up here on this other rocker switch. If I hold it, right, back up. So quick up, quick down are the driving lights and running lights, front and rear. And then, yeah, long up and down are sounds. So down is the horn. If I hold it down, get the horn. And then the buyer sound module also, if you get the optional CD with it that comes with their sound library, it comes with this huge library of all kinds of other sounds that you can program to show up randomly, as I have for some, or on various kinds of commands. I have one of them rigged up here to the rocker switch, so for a long press up, I get a fart. And I think that is awesome. I also have some more boring but very pragmatic features set up. The buyer sound module allows me to configure a volume control to one of these switches, so I have it set for a long press up and down, increases and decreases the volume, and a short press up toggles the backup alarm. To all my neighbors, this one's for you. So to recap here, there are two main challenges with this project. One is the physical mounting of the module, and I settled for this location in the back of the cab right here. And to make that work, I had to make myself two new mounting holes for a little metal shield that's inside the cab that hides this compartment, segregates this compartment from the rest of the cab so that you can't just see through it through the windshield. A little bit tricky, but not too big a deal overall. The other tricky part really is more tricky, and that is because the outputs for the lighting are not the same between the two sound light modules. They are both a digital output, and I'll explain what that is, but they operate a little bit differently, and so it's not a one-to-one swap when changing out the modules. And if not done properly, it'll result in burning out the LEDs very quickly. So a little bit about the output drivers used for LEDs. So the old school type, analog, will vary an output voltage between some supply voltage, say we have 12 volts, and 0 volts or ground. So, you know, if you graph that, it's pretty obvious. We've got time on this axis and voltage on this axis, and if we increase the voltage over time, and our 12 volt maximum is here, we might just have something that looks like that, right? Pretty simple. A digital output is a different animal. And these kinds of systems use digital outputs because they're small and inexpensive to manufacture. Analog outputs are physically larger, less power efficient, so they generate more heat, which means that they need to be even physically larger in order to accommodate that power dissipation, in order to be able to get rid of that heat. So they use digital outputs, and digital outputs will switch between only two states. If we have time and voltage, and this is our 12 volts right here, our digital output can be either at 0 here or at 12, at whatever the battery voltage is. And it can only switch between these two states. So how do we get brightness control? Well, they do this with a technique called pulse width modulation, or PWM. And this is a technique for gaining an apparent brightness control to the human eye by switching a light or an LED on and off really fast and varying the duty cycle. And what I mean by that is varying the ratio of the digital on time to off time. So, for example, if we have a PWM output that is operating at, say, 100 Hertz or turning on and off 100 times per second, and it's at the 25% mark, meaning we're at 25% duty cycle, and it's on 25% of the time. So for this is time 0 right here, this is time 1 complete cycle. So we'll divide that into quarters. That would mean that we might come out here to time 0.75, turn on, and turn off again at time 1. So over the course of one complete cycle of that 100 Hertz waveform, we're only on for 25% of the time. And under the right circumstances, this can appear to the human eye as a 25% brightness. If we want 75% brightness, we might do something like turn it on 75% of the time. So we'll turn on at the t equals 0.25 mark and stay on all the way out to time 1, or 1 complete cycle. So we're on for 3/4 of the total cycle time. Now, if you look at the power and energy in this circuit, we really are at 25% and 75%. But there's a catch here, and that is that the voltage still swings between 0 and 12 volts. And this is a problem for LEDs. So LEDs, light emitting diodes. A diode is the simplest semiconductor device. It has two terminals, and it functions as a sort of a one-way valve for electricity. And the plumbing analogy actually works pretty well if you imagine it as kind of a crappy leaky valve, a kind of a crappy leaky check valve. The analogy actually holds really well. The symbol for a diode is, for a basic silicon rectifier, is something like this, and for an LED we'd have these extra arrows out here indicating that it emits light. And in this diagram, current flows this way. This is the negative terminal and this is the positive terminal, and when it is biased this way, current flows. When it is biased the opposite way, with this being positive and this being the negative terminal, current doesn't flow. In an ideal diode. Real world diodes are a little different. When you look at a data sheet for one of these devices, there are a couple of primary parameters that stand out. So one is the forward voltage. The other is the forward current. For an LED, we're not really going to worry about reverse voltage and stuff like that. We're going to make the assumption that we're using it within the limits of its capabilities. So forward voltage on an LED. So for a typical white LED, like what might be used in an RC vehicle, the forward voltage will be something like 3.5 volts. And the forward current will be 20 to 30 milliamps, depending on what kind of diode it is. We'll call it 20 thousandths of an ampere. And these numbers are really important. So when we connect a diode in a circuit here, we've got a positive voltage supply, we've got a diode, our LED, and we've got negative voltage or ground. And so what this is saying is that if we put 3.5 volts across here, across this diode, we will have approximately 20 milliamps of current flowing through it, and it will be producing light. Now typically, this is not a typical forward current. This is a maximum forward current. And for reliability reasons, we want to stay away from that number a little bit. And the reason that this is a challenge in PWM systems is that our output voltage here is swinging between 0 and 12 volts. So when you put 12 volts across an LED, it's going to fry, even if the duty cycle is only 10%. It can't handle that. So what we have to do is find a way to limit the current. And this is really where these two numbers come in, is doing this calculation. So our total supply voltage, we'll say for a 3S pack, is going to be 12 volts. The voltage that we want across our diode is going to be approximately 3.5 volts. How do we make up that difference? Well, let's put a resistor in series with it. This way we can limit our current. But how do we pick the value for the resistor? Well, to do that, we start with an assumption. We want to set this current at some point just a little bit under this 20 milliamps. We want our LEDs to be as bright as possible when the brightness is turned all the way up, but without compromising the life cycle of the device. We want it to last a long time. So let's set that at 18 milliamps. So we have a 10% margin. Now for choosing the resistor value, we use Ohm's law. V equals IR. The voltage equals the current multiplied by the resistance. We know what the current is, 18 milliamps. We don't know what the voltage is just yet, and we want to solve for the current, for the resistance. So R equals V over I. We know I, so what's V? V is going to be the voltage across this resistance. Call it VR. V sub R. So V sub R equals our supply voltage, 12 volts, minus the LED voltage, 3.5 volts. So that equals 8.5 volts across the resistance. So now R equals 8.5 divided by 0.020, which equals 425 ohms. So a resistor value of 425, 5, now you probably can't read that because it's all mangled and really small, will put our current through the LED during this on time at 18 milliamps, which is within the safe zone for this LED. There's one more part to this, and that other part is power. All electrical power consumed by any electrical circuit in the world is converted into heat, and that includes all of the power that is dissipated in our series resistor. And the LED for that matter, but in the LED it's not such a big deal in this case. So power, measured in watts, is the voltage multiplied by the current. And our voltage, if we're looking at power dissipated in the resistor, our voltage across the resistor is 8.5 volts, and the current through the resistor is 18 milliamps. So our wattage is 8.5 multiplied by 0.018. Is 0.153 watts, or 153 milliwatts. This is an important number because this determines the physical size of a resistor that we need. For a single LED, we're dissipating 153 milliwatts. A typical axial through-hole resistor is a 250 milliwatt part, or quarter watt. So this is fine for a single 153 milliwatt load. You want to leave some margin, usually about 2 to 1, to make sure that the resistor doesn't get too hot. As I said, all the power that is dissipated here is converted into heat. And if you exceed this power rating for the resistor, it will get hot and can be damaged, and can damage other nearby circuits or devices or wiring. And it can melt things. So what happens when you have a circuit with 4 LEDs on it, or 8, or 10? You're looking at multiples of this power. So you need bigger resistors. In the case of my wheel loader, I have a circuit with 4 LEDs on it, and another one with 6 LEDs on it. So if we round this to 150 milliwatts, we've got 600 and 900. So for this one, Resistors will typically come in increments of quarter, half, 1, 2, and 5 watts. So we need at least a 1 watt resistor for this part, and probably a 2 watt resistor for this circuit. And there are some tricks you can do by dividing this power dissipation between two different resistors. So you could put two resistors in parallel, for example. Like this. But then they need to be at twice this value in order to have the same total resistance. So you need 850 for both of these. But you'd have half the power dissipation in each one, so sometimes a circuit like this could be advantageous if you need really small components. What I did, I just put 1 and 2 watt resistors in there and took a chance that I'd be able to make it fit, and it worked out. But this is really important so that you don't burn stuff up. Now, circling back to the original issue, the original sound module did not have any series resistance for the LEDs. So when I changed to the new sound module, I needed to add this series resistance to keep from burning up the LEDs. And this is something that's not always so obvious when getting into a project like this. This has been another fun and challenging project. Thank you for joining me. I've had a pretty good time with it. If you like what you've seen, please consider liking and subscribing. Until next time, project on, people.